Hi, in this particular video we'll be talking about a miscellaneous technique to find out summation of the form. Let's say you're given n as an input up to 10 to the power 12 and the function that you need to find the value of is n by 1 floor cube plus n by 2 floor cube plus n by 3 floor cube up to n by n floor cube, and you need to find this particular value. And let's assume that for now these values don't overflow. Like, even though for this particular value it will be difficult to save these values in a integer, but let's assume that overflow is not a problem for us right now. Okay, how do we compute them efficiently? That's the main thing. So there is an obvious order n approach for this particular problem, that you can loop from 1 to n, which should give you, let's say, you calculate the value of n by 1 floor and then cube it, calculate the value of n by 2 and cube it, and keep on adding. That's an order n approach, and that will definitely TLE on like this particular input, right? So we want to do it better than order n. So how do we solve this particular problem in less than linear time? So before we look into the solution idea for this particular problem, let's first try to look into what are the different values this n by I function is taking when n is equal to 12. Okay, so 12 by 1 would be 12, 12 by 2 would be 6, 12 by 3 would be 4, 12 by 4 would be 3, 12 by 5 would be 2, 12 by 6 would be 2, 12 by 7 would be 1, 8, 1, 9, 1, 10, 1, 11, 1, 12, 1. Okay, so these all values would be there. Now if you note the number of distinct values it's taking, so this is going to be pretty less, right? Like only 12, 6, 4, 3, and then a bunch of 2's and a lot of 1's, right? In fact, we can try to generalize this particular idea, that what are the number of distinct values this take. Okay. So let's talk about this function f of x equal to some given input n by x. So let's talk about what is kind of like the number of values this particular function takes, or how does this function looks like. Okay, so if we try to look into the values that it takes, so at n equal to 1 this would be n, next time it will decrease to n by 2, then by n by 3, and then after some point you will see that some values are coming continuously same for, let's say, 4, 5, 6, all of them are getting same value, and then from 7, 8, 9, 10 these are getting same values, then 11, 12 are getting same values, right? So there are like trails of continuous value in this function that are getting formed. Okay, and this is the part that would be taking into consideration to decrease the time complexity. So there is a very nice harmonic lemma that comes up for these particular forms of expression, and the harmonic lemma says that for any n, the number of distinct value n by x takes is bounded by order root n. Okay, the number of distinct values n by x can take is order root n. In fact, it's bounded by 2 root n as well. Okay, so it's order root n. So if we can somehow enumerate on these root n values quickly, we could find out each of the the summations very fast, right? Because we know that a lot of these continuously would have same values, then a lot of these would have same values, and so on, right? So let's talk about, let's say n by I is some particular starting point. So in this function, let's suppose 7 is I. Okay, 7 is this I. Now till what point this particular value would be same and then the next value would change? If we can somehow find out this last value, we would be good to go with the problem, right? So how do we find out the last value x such that n by I floor is equal to n by x? So it turns out we can find the value of x from this expression to be floor of n by I. Okay, so n by I is over here, this is a particular number, so you just x will be equal to floor of n by this, whatever this value is, y or n by I. Okay, so this is the highest x till which it will take the same value. Okay, so we can, using this, we can devise a technique to solve this kind of problems where you have a lot of n by I in the function, that okay, you start from I equal to 1 and you calculate the last till which this particular I extends, right? So the value of n by I will extend from I to L of A, so you calculate L of A with what we discussed over here, this x is L of A, and we can process the range I to LA together and then make I equal to the next value from L of A, right, until we reach the last value in the range. Okay. So this is the loop that we'll be using, and this loop has order root n number of operations because we know that this will iterate on different values of n by I, and we know from harmonic lemma that okay, there are only order root n number of distinct values that n by I can take. Okay. So this particular loop would solve the problem in order root n. So how do we use this for this particular problem? So we would have, let's say, answer equal to 0, integer cube equal to the function to return a cube of numbers. So currently things will not fit in integer if n is up to 10 to the power 12, but we don't talk about fitting and other things right now. We will take mod or something like that in case it's not fitting, but just the logic part would be that we use this particular loop. So from I equal to 1 you start, so you know that from I to LA all the values are same, so there are LA minus I plus 1 number of values, all of which take the same value. Whatever the value of n by I is, that is the same value of this floor is equal to n by I plus 1 floor and so on up to n by LA. So all of these we can replace by cube of n by I, right, n by I, and this particular cube will occur LA minus I plus 1 number of times. Okay. So this particular loop is in order root n. So this particular function would compute this particular expression for n up to 10 to the power 12 in order root n, which is sufficient for getting past the time limit, right? So in short, there is this nice harmonic lemma that you should know about in some problems, that n by x takes only root n distinct methods, root n distinct values, and to find the last value which is same for any particular I, you can use this expression. So we can use this particular loop over here to enumerate on different values of n by I and ranges which corresponds to that particular value very efficiently. So that's all for this video. See you in the next one.